Hi all, I am here with my new video on chemical bonding and molecular shape. Let's start. In this video, we will learn rules to draw the Lewis structures of covalent molecules and polyatomic ions. Here is a set of 5 rules that can be used to build the Lewis structures of molecules and polyatomic ions. They are as following. First, count the total number of valence electrons in the molecule or ion. To better understand this, we can take example of water H2O molecule. It has 8 valence electrons, 6 from the oxygen atom and 1 from each hydrogen atom. Second, if the particle is an ion, add 1 electron for each negative charge, subtract an electron for each positive charge present. For example, water molecule is neutral, no electrons are added or subtracted. Third, draw a skeleton in which all of the atoms are connected by single bonds. Try a symmetrical structure first. A single bond represents a pair of electrons that belongs to both of the atom it connects. Structure of H2O can be drawn as below. Fourth, complete the valence level of each atom in the molecule by adding unshared pairs of electrons as necessary. The valence level of a hydrogen atom is complete with 2 electrons. Assume that all other atoms are complete with 8 valence electrons. Example of H2O, the valence levels of both hydrogen atoms are already complete. The oxygen atom needs 2 unshared pairs of electrons. Fifth rule, compare the total number of electrons in the skeleton with the number you arrived at in step 1 and step 2. If they agree, you are done. In this example of water, the numbers of electrons agree and our molecule is built. Network solids. Certain atoms like carbon are able to form covalent bonds with other like atoms in a three-dimensional arrangement called a network solid. The three-dimensional network solid that consists of carbon atom is known as diamond. Another allotrope of carbon, graphite, also exists as a modified network solid, but it consists of a series of loosely associated two-dimensional sheets. Other network solids include silicon carbide, SiC, and silicon dioxide, SiO2. Network solids, by their very nature, do not form individual molecules. Metallic substances. Metals have 4 specific properties. Luster means shine, conductivity, malleability, and ductility, which arises from the way in which metal atoms bond to one another. Atoms that form metallic substances have low ionization energy and relatively unoccupied valence levels. These conditions allow the valence electrons the freedom and the room in which to move, and the valence electrons are delocalized over the entire metallic crystal. As a result, the valence electrons do not belong to a single atom, they belong to the entire crystal. The remaining part of each atom, which consists of a kernel, a positive ion, forms the backbone of the crystal. Following diagram is representing a section of a metallic crystal. Dipoles and polar molecules. In a polar covalent bond, shared electrons are attracted more by the atom which has higher electronegativity than another atom. In that case, the negative end of the bond is centered around the atom with the higher electronegativity. The positive end around the atom with the lower electronegativity. We call this imbalance a dipole. The positive and negative ends of the dipole are represented by the symbol del plus and del minus respectively. The HO bond may then be represented as follows, where del plus is around H and del minus is around O. That the positive and negative ends of a dipole are not real charges because no electrons has actually been transferred between the atoms. The dipole represents only an unbalanced charge distribution along the bond. In certain examples, polar covalent bonds in a molecule will cause the entire molecule to have unbalanced charge distribution. Such molecules are affected by electric fields and known as dipoles or as polar molecules. Example, hydrochloric acid, HCl. All molecules with polar covalent bonding are not necessarily polar molecules. Whether a molecule is polar or non-polar depends on the symmetry of its electron charge distribution. For example, H2O is a polar molecule because its polar covalent bonding and its band shape give it an asymmetrical, unbalanced charge distribution. In contrast, CO2 is not a polar molecule. While both carbon-oxygen bonds are polar covalent, The linear shape of the molecule gives it a symmetrical balanced charge distribution. As a result, any dipole arising from one of the carbon-oxygen bond is cancelled by the other, as shown below. Summary of polarity and molecular symmetry. We can summarize it as following. Molecules containing only nonpolar covalent bonds and all monoatomic molecules are nonpolar. Example: helium, argon, neon, nitrogen, and carbon. Molecules containing polar covalent bonds with symmetrical charge distribution are nonpolar. Example: carbon dioxide, BF3, CCl4, and BCl2. Molecules containing polar covalent bonds with asymmetrical charges distribution are polar. Example: hydrogen fluoride, H2O, ammonia, SO2, and N2O. In our next video, we will learn about intermolecular forces, van der Waals forces. Please like and subscribe to watch new videos, and it helps and inspire me to make more videos and reaching out more kids like you. Thank you. Bye bye.